So, error probability. First question. Number of something, for example, number of people who found an anxiety drug effective out of 100. Is that the same as saying the probability of people who found the anxiety drug effective? So, 1, the number of people. 2, probability. Are they the same? Savannah says no. Or not?
Well, just based, I don't know, in our last problem, we did the number of people as n, and the probability is just p, so like a percentage.
It's a percent. So it's a percent simply means part of total, correct? So if I had 200 something people, out of those total 200 people, how many found the drug to be effective? That would be a probability. So we're not going to deal with the number of false positives, number of false negatives. Rather, we're going to look at alpha, which your book calls it P. PR stands for probability. It is the probability of type 1 error under the assumption that the norm is true. This is a key part. Since the very first day, this part has been the case. When I started hypothesis testing, I said our reference is the norm. That's what we're going to assume, and we're going to see how far the evidence is going to take us away from the norm. That is the fundamental concept of hypothesis testing. So the chances of making this error, in other words, a false positive, if you do 100 tests or 1,000 tests, is alpha. We can also call this as false positive rate. Let us see whether your book does a problem on calculating these. I don't think so. So I don't want to make things complicated. So for now, this is good enough. Next letter, beta. Beta, if you have to take a guess, what is beta? Type 2 what, Elizabeth?
The probability.
Okay, let's complete the sentence.
The probability of getting type 2 error if the norm is true.
Okay. Are you conserving energy?
Maybe.
So the probability of a type 2 error under the assumption that the norm is true. Well, now, let's simply have a definition of alpha and definition of beta. Okay, so as I mentioned, the goal is to make that 0 by fixing this at a reasonable level. At reasonable level, we have seen this before. Your book calls it conventional levels. 0.05, 0.01, oops, and 0.1. I didn't like it in order. That's okay. all of our problems that we did in the past, previous chapter, we used these boundaries, yes? These gave us the cutoff score. We used the cutoff score to determine and obtain a conclusion. So this plays a part. We did not talk about beta at all, right? Even in chapter 4, when we did those examples, this never came into play. I ended my last class by saying that this is an abstract concept. Because, for one, no one knows what the truth is, correct? If you don't know the truth, how can you write all this stuff? So it has to be an abstraction. Two, I don't have a total here. In order to do that, I need to have data. So again, it becomes theoretical. So what is the point of this? Later this semester, all of this is lead into what we're about to do in terms of statistical testing. When we do a test, why should one rely on the test results? Why should you take it for granted, even if it is true? Or even if there is evidence toward whatever that you did, and you have enough support from data, why should you put faith in it? Scientific process. So the scientific process works in the sense you have a hypothesis, you collect evidence, you come to a conclusion, reassess if you get new evidence, see if your conclusion changes or remains the same, you repeat the process. Yes, of course, peer review plays a part in it. Why should you believe any of the tests that would come up soon in this course? Now, I think this is what we would do. I proposed a test for my dissertation, but it is in higher dimension. So the simple concept there, since we don't know the truth, we are going to simulate. We've all heard of simulations before, yes? Using a computer, we're going to simulate not just 100, 200 times, you would simulate it, repeat it over and over for 1 million times or so. So let's say I proposed the test for a scenario. I came up with this test. I want people to use my test for their research. Good. Before I present that my test is valid, I've got to prove to my peers that this is a valid test that you can rely on, correct? Yes. So I propose a test, and this is what I would do with my simulation. I will fix this value for each of those cases and use my numerical stuff, theory, whatnot, and see if this becomes 0. But in other words, if that becomes 0, the probability of type 2 error is also going to be 0. Agree? So I'm going to fix this and see if that becomes 0. If it did, for the appropriate cases, then my test is doing a good job. Do you agree? Going back to test trips, let's say we fix the false positive rate at 1%, and the people who manufactured the test strip is going to repeat this over and over and over again. And maybe they did it 1,000 times, 100 times. And out of those 100 times, it never produced a false negative. It became 0. then I could say that the test strip is a good test strip. Do you agree? Same thing. I propose a statistical test. I fix this at a certain value, repeat it several times, and if that becomes 0, then I'm comfortable that this test could be used. Good. So every single statistical test that you will encounter in this class have been verified through a process and guaranteed to work under the right circumstances, which is why we use them in our day-to-day lives. Good? So, who does this? Someone like me. And we just provide you the test so that you can use it in real life. Are we clear? Okay.